Hello, 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 hello. Is it not? Is it working? No, it's not. Hello. Okay. So I hope it stabilizes. All right, let me try this so I don't need to, yield for like 3 hours. Does it work? All right.
Yeah.
Okay.
What's the screen you share is the
Presentation mode.
Yeah,
Let me try this. What about now? Okay, it's good. All right. Well, welcome back. So it's been like 2 weeks, 1 week due to MT Martin Luther King and another week due to the snow. All right. So in today, so far the first week we went through some basic introduction. Then the second week we went to pruning, right? So in this week, tonight I'm going to introduce another sparsity technique. You probably heard of it, quantization. If you already take, signal processing or um, my microcontroller class, you probably already at least heard of the term quantization, right? So the idea of quantization is using a lower bit of data representation to replace the high precision data. So in today's lecture, I'm going to first just quickly go through all these data representation types. So I hope you should at least have some knowledge about this. How many of you like don't have any knowledge on, all those data types, floating point, integer, fixed point? So, okay, so everyone, so you never. Okay, so I'm going to I'm going to go through the data types, but if you probably like fairly quick. So if you have any questions, just let me know. Okay, feel free to raise your hands. So after I introduce the data types, I'm going to um, talk about the basic concepts of neural network quantization, and there are three types of quantization we are going to talk about today. So this KV-based linear quantization, we're going to spend quite a bit of time on linear quantization, then we are going to talk about this binary or ternary quantization. Okay. Right. So data. I need to so data type. So so less bit width to represent the data means that less energy. So this one just gives you the kind of the comparison between 8-bit integer number, 8-bit integer add. It requires every 8-bit integer add requires 0.03 picojoule. While if you look at the 32-bit floating point add, it's going to be like 30 times of more energy to do the same operation. Same for similarly for multiplication. So if you look at 8-bit integer multiplication, it's a 0.2. But if you look at 32-bit floating point multiplication, it's a 3.7. So that's like 60 times of higher energy consumption. So how should we make them more efficient? So we want them to use the less bit width to represent the data, right? So I'm going to just quickly go through the numeric data types. So we have one. You should have already learned about all these unsigned integer, signed integer, choose complement number. The text is a little bit scrambled. So I prepared the slides in the Google Doc. I think somehow the format is a little bit off. Any questions about this? Have you already learned about this, right? At least. Then we talk about fixed point integer. I'm sorry, fixed point number. So we have this integer part with the fraction part. And that's how we use this to represent the data. So you can see that basically each digit represents a count of 2, right? So if it's the fraction part, it's going to be negative 1, 2, 3, 4. If it's the integer part, it starts from 0, 2000, 0, 1, 2. And the most significant bit is the sign bit. All right. So just to refresh our memory, so for fixed point numbers, when we are doing the addition and the multiplication, we can use the integer operation hardware to do this, right? Because for example, like when we are doing fixed point number add, you can just use an integer adder to do the operation. Because basically you have this implied the decimal point in your head, and that you just use the integer add or multiplier to do the multiplication. Any questions on that? So that's that. Then we talk about floating point number. So we have this, exponent fraction. This exponent part has a bias and the fraction. So any number can be written in this form and then converted. For fraction and exponent, each of them convert to binary number. So that's floating point number. How do we present 0? So so you have kind of have 2 zeros. So so this is like the normal number. So we know like for floating point number we have a range, right? So they have this positive number from minimum to the maximum, also negative number from minimum to maximum. So then also in this IEEE standard, we define this subnormal number, which is within the small range. So we do not have the 1 plus the fraction; it's just the 1, and we fix the exponent to be 1. I'm sorry, to be 0. So that gives you another set of number that you can represent with fixed point number. What is the largest positive subnormal number? Basically, you are setting all these bits to be 1. That's the largest possible subnormal number. So what is the smallest? What is the smallest subnormal number? All 0. Yes. So if it's all 0, then that's going to be what? that's just going to be a zero, right? So but for subnormal number, the smallest number you can represent basically is what is that? Remember I have that slides. Oh, I'm sorry. So this is the smallest, the subnormal number, which is the least significant bit to be one. So that's the largest subnormal numbers. So that's just like all these different numbers, different. And we also have all these, positive infinity, negative infinity, not a number representations. So this picture clearly shows, different, this normal value represent from here all the way to here, and the subnormal number is representing from this part to this part, right? So these should be already been covered in the whatever class that it was. So if you compare, well, let's first compare the first two number system, this floating point 32 and this floating point 60. So the blue part is the exponent, the yellow part is the fraction part. So basically the exponent width is going to give you the range, right? And the fractions give you the precision, like how precise you can represent a number. That's the general idea. So then like Google has this brain full BF number. So what that means is that while the same 16 bits, instead of using only 5 bits as the range and like all these bits as the precision, we can use 1, 2, 3, 4, 5, 6, 7, 8, 8 bits as the range and another 7 bits as the precision. But the reason apparently is that when you are training a network, people find out that this way we don't need that much of precision, but we do need more range. So this way we can still capture the capability of the network, but using the same 16 bits. Does that make sense? So that's just some this is a conversion. Also, like this should be well covered before. So I'm going to skip this. Oh, I think the point here is that compare a standard IEEE floating point 16, which you have a 5-bit exponent, 10-bit fraction. But this is the BF type, where you have 8-bit exponent and 7-bit fraction, just can kind of give you an idea of different representation, even the same value that gives you different, the same floating point value that will give you different totally, the value actually represents, right? So that's that, and the NVIDIA also has its own definition. So this floating point 8, you have using 4 bits as the exponent and 3 bits is the mantis. So and here it's using 5 bits as the exponent and 2 bits for the mantis. So that's just different, and you can see that like basically we don't need that kind of precision. We want more range. We want to represent with that 8-bit number. Okay. So that's that. What else? And this one gives you like just a very visualized illustration of what does that like? What are the differences? So like this, the first one shows the integer, 4-bit integer, right? So that's the range you can represent. Like that's the range and the precision. But if you are using these 4 bits to represent as a floating point number, so you can see that even though it's the same number of dots, but the dots on these axes like it moved, right? So the range, both the range and precision actually changes. That makes sense? And this one is E1 M2, and this one E2 M1, and there's E3 and M0. You can clearly see that like when you are moving when you are allocating more bits to the exponent, the range actually increases, but the precision decreases. Okay, so that gives you a very good illustration of what happens when we're allocating the different number of bits to the exponent and to the magnitude. What is quantization? So this should be in one of the signal processing course you took. Quantization is the process of constraining an input from continuous or otherwise large set of values to a discrete set. This is like just a signal, and we know that the signal is a continuous data, and all these data there are infinite number of data in this wave, right? But when we want to no matter if it's like a sound wave or whatever signal you are capturing, we need to digitize it into the computer, right? Because the computer can only store like discrete numbers. So when we are doing that, we need to find, for example, like here, like to represent, let's say like if I want to represent the peak of the wave here, but like with a limited number of bits in the computer memory, we don't have that kind of capability to capture that exact number. So we end up using the number that closest to that number. Okay, so we can use like, for example, like this yellow dot to approximate that number. So the result is that we get a close enough number, but it's not the exact number. So there is a quantization error over here. Okay, so that makes sense. So if you just look at all these yellow dots, it can kind of like give you the shape of these waves, right? But it's not exact. So it's approximation and there's the error in it. I think this one gives you this just give another illustration. Basically says when you are quantize it, you are going to get pixelation. So quantization for the neural networks. So today we are mainly going to talk about three different approaches. This k-based quantization, linear quantization, and this is binary or ternary quantization. When we are talking about quantization, there are two things to pay attention. So first is like when you are quantizing, apparently you are reducing the storage, right? And the other hand, you also reduce the computation. But both like for all these different quantization methods, it's not necessarily that you are reducing both of them. And you should see what I mean by that. So if you look at the original matrix, the weight, let's say, if this is a weight matrix, originally it's a floating point. So it's stored in the memory as a floating point number. It's a 32 for each digit, for each number, right? We need a 32-bit of storage for each digit. And all these calculations, if you want to multiply this matrix with another matrix, with another vector, all these calculations are floating point arithmetic. Means that like it's more expensive to do, right? So the idea is that we want to quantize this so that while we can reduce the storage and reduce the computation. All right. So first, let's take a look at the k-means space of quantization. So for k-means space of quantization, the storage is going to be integer. So you can see the matrix itself becomes integer. But we have additional code book, which is floating point number. And because we have this floating point number, the computation eventually is still floating point. So we are not doing integer computation for this kind of quantization. Okay, so let's see why is that. So for this k-mean base, like we want to, let's say like we pick. So there are total 16 numbers, right? And we want to find like, let's say 4 numbers that are closest to each other. Let's say like 2.0, 2.12, 1.92, 1.87. So we've got those 4 numbers, they are the largest 4 number, they are close to each other. We can kind of using an average number or like the closest integer to represent that number. So the difference between this number and this number, that is the quantization error. Make sense? So easy. So if you do that, for every 4 number. So you end up like 4 green number, 4 blue number, 4 pink number, and then 4 orange numbers. I'm sorry, actually, yeah, 1, 2, 5 orange numbers. Okay, so you got that. So you create a code book like this. Okay, so don't look at the others, just look at this one. So we create a code book as 2.0, 1.5, 0, and -1. Okay, and then the original matrix now it just becomes an index to the code book. And this code book, we call this centroids. So if you look at the 3, what that means is that this is indexed to the code book, which is then that means that it's 2.0. Okay. And you can see here, originally it's 2.12, now it's also 2. Originally it's a 1.92, now it's also 2. Okay. So in this way, essentially we are creating this code book and indexes to the code book to do the quantization. But why are we saving? Are we actually saving? We can do a little calculation, right? So if you do this for these 16 numbers, each number is a 32-bit floating point number. So if that's the case, that's the total storage. And with this, the code book, of course, they are still floating point number. So we need 4 numbers, each is 32-bit. But for the indexes, because we only need like index 4 entries in the code book. So the index, each number in the index, while in the matrix only need 2 bits. Okay, so the 2 times 16 gives you 32 bits. Okay, so that gives you, if you're adding the indices and the code book together, that gives you 20 bits. So that's like 3 times smaller. Okay, so that's just the memory storage. Assume a n-bit quantization that the number of parameters is. So that's kind of the how much storage you can save. Okay, but then like if you look at this, say, oh, so now I have this. If I reconstruct the weight, this is what I reconstructed, right? So 2.09 now it becomes 2, okay, and 1.21 becomes 2, right? So if we deduct this matrix from this one, so we subtract this number from this matrix, we got this quantization error. Okay. So when we are coming back to these slides later, but so once you have this, we know that in this network, when you are training the network, you are going to tune the weight, right? So when you are training the network, you are going to tune the weight. What happens is that the gradient is going to be grouped again. It's also it's also going to be grouped, and then like the average. While there are different ways, either you take the maximum or the average or the minimum. So you reduce this to this and you apply that gradient to this centroid. You got a new centroid. That's the way to tune this k-mean based quantization. Okay. This one shows the accuracy drop when you are compressed how much the model size ratio after compression. So the yellow, the dots give you this chart. But remember last week when we talked about pruning, we also showed you a chart like this, right? So we show you like when you are prune different percentage of the network and like how much accuracy loss we have. So if you put them onto the same chart, that's kind of gives you the idea. And well, the natural question is, well, can we add them together? And the answer is, of course, yes. So you can add them together to give you, the best results. So you can see that like, while you can compress it way smaller, like without even sacrifice any accuracy. Right? So that's very impressive. So this one gives you this illustration of this the x-axis all these weight values. So y-axis is the count. So for example, like 0, there are that many number of zeros, but this the peak is like, let's say like 0.03-ish. And you have that many of that value, and this is like how to 10 power to 3. Okay, so after the quantization, what happens essentially is that while we do not have like all those values, discontinuous values, right? Because we delete some of them. And what do? We delete them and we approximate them with some of these centroids, right? So this end up like all these, you can see that end up like all these centroids are going to be, higher because we are essentially delete some of them and push them towards the centroids. Does that make sense? And then like sometimes after you quantize it, you're going to retrain it, retrain the network to gain some of the accuracy, recover some of the accuracy back. So that's kind of gives you the distribution of the weights and the number of counts for all these weight values. So a natural question is also like, now we know that we can quantize all these numbers, but like how many bits do we really need to do the quantization? 2-bit, 4-bit, 8-bit, or 16-bit, right? So so they did this paper did some of these experiments. So basically we want to see that, how many bits, what is the minimum number of bits to maintain the original accuracy? So here you can see that for this this is top 5 accuracy. So you can see that with only 4 bits instead of 32 bits. Okay, with 4 bits of quantization, we can almost retain the original the accuracy. Similarly, for even for top 1 accuracy, 4 bits is kind of good enough. And for this is for the number of bits in these are for the convolutional layers. Usually they need the 4 bits. For all these fully connected layers, 2 bits can maintain a very good accuracy. So after you do this quantization, after you have this distribution, right now, when we are coding it, this paper they did something else. They did this Hoffman coding. So anyone still remember what is a Hoffman coding? So a Hoffman coding is a compression method, right? So you are using anyone? What's the idea of Hoffman coding? So when you are compressing it, essentially you have the accuracy of each of the values, right? So because all these values say like if you have more number of counts, it means that like you have more of that value in this network. And therefore, like you want to use less bits to encode the frequent values, right? So that like the total number of storage is reduced. Does that make sense? Okay. No? Does that make sense?
Just repeat that one more time.
Sure. So, well, we need to store all these values, right? We need to store all these values. If we just simply using for just encode them with a uniform like 4-bit encoding, everyone is 4-bit or everyone is 8-bit, right? So instead of using this uniform encoding, how about for example, for these two, like we figure out like these are a more frequent values, then we are using fewer bits to encode it. And these are the little values, so we are using a longer bits to encode it. So therefore, the total number of bits in this whole network got reduced. Okay, so that's the idea of the Hoffman coding, right? So combine everything together. So we can do well, we first go through the pruning, then we go through the quantization, this k-mean base, and then using Hoffman coding to finally code it. And the paper claimed they can retain the same accuracy with almost 50%. I'm sorry, 50 times of reduction of the original weight. So this is a decompression paper. So that was like, published more than 10 years ago. They also did some experiments with all these different, compared with all these different networks, the net, AlexNet, VGG, GoogleNet, and ResNet. And this shows the compression ratio for these networks. And this the last two column shows the accuracy comparison, and you can see that they are maintaining almost the same, sometimes even higher. Actually, most of them are higher. You can see that 0.36, 40, 20, 26. So most of them actually you have higher accuracy with much smaller model size. They tested on this squeeze net. So this is the experiments for the squeeze net. They have this, well, compared with AlexNet, squeeze net is already very small, right? So with the squeeze net is already much smaller than AlexNet. And then with the deep compression, they further compress the squeeze net another 100 times. I'm sorry, 10 times. So that becomes like 500 times smaller. Okay. And you can see that the accuracy actually is higher. So that was a very impressive result. So during the computation, like during the inference, now the process is shown in this flow chart. So basically, we need to look up the table. So we needed a code book. We need to quantize the weight, and we decode it. Basically, it's a fetching process. And then, like after you recover, reconstruct the weight. The weight now is actually a floating point number, right? Because if it's 3 times 3, then you find 2, it's a floating point number. So the weight is still a floating point number. And then you are going to multiply with another floating point number. So you can see that when you are doing a convolution or the fully connected the fully connected layer, the multiplication are still between 2 floating point numbers. Make sense? And addition and everything. So the whole calculation is still floating. We still have to use floating point hardware. That makes sense. We only reduce the memory storage, but not reducing the computation with this K-mean method. Okay. Okay. So that's why here. So the computation is still floating point. The weight is integer, but the code book is floating point. Okay. So next, we are going to spend a bit of time on this linear quantization. So linear quantization is another idea of quantization. So again, let's come back now. Forget everything about K-mean. This is a totally new method. So with the same, floating point matrix, what a linear quantization means is that it's taking, it basically is doing a linear transformation. And what is a linear transformation? So, for example, like for this integer and all these 2-bit integer matrix, you can do a shift and a scale, and you get this matrix. And this is all unit. Like this is 0. This we call 0 point. This is called scaling factor. So and then we got this matrix. And if you compare this matrix with this matrix, if you just subtract this matrix from this one, and that's the quantization error. Okay, so that seems really cool, right? Because now we do not have we get rid of the code book, right? So we don't have the code book. We only have a integer with 2 fixed numbers, 0.1 the scaling factor. Right? Make sense? So apparently this is, well, even at the first look, it's more efficient than K-mean. But the question is, well, then how do I know like what 0 point should I use? And what kind of scale should I use, right? So that's the question. So we call this, so the original matrix, which are floating point numbers, we quantize this into a integer matrix. We subtract a 0 point, this is Z number, and then we multiply with a 32-bit floating point number. Okay, so that's the key idea. Any questions so far? All good. All right. So what does it like the mapping actually do? So the red dots represent the quantized value, and the blue number, which is the floating point range, right, represents the original value. And when we are doing quantization, essentially when we are doing this linear transformation, this affine mapping, what it does basically you are mapping this range of data into this range, right? This discrete and fixed number of dots. Okay. And when you are trying to, and when you are really trying to do this, apparently when you are having this subtraction Q minus Z, if you look at the chart, essentially we are kind of align the 0 to the 0. Okay. And when you multiply S, it's kind of like you are scale the number up to the maximum. We are scale the maximum number of the Q to the maximum number of the R. Does that make sense? So that's kind of the meaning of this Z and this S. And then like if you look at the and then if you expand this, so apparently when we are doing the mapping, what we want is that the R max equals to S times Q max minus Z, right? And the R min equals to this Q min minus Z times the scale. So that's the whole mapping, right? We just plug this into this. And if you do this maximum subtract minus the minimum, you got this equation over here. Okay. And then like if you put S, you take S out, so you got S essentially equals to the R max minus the R min divided by Q max minus Q min. So that's how you determine the scale. Does that make sense? So by doing this, essentially, we can determine, once we know the range of the floating point number, the original, the weight, the range we want to quantize, right? And the range that we quantize to, then you can kind of get the scale over here. So once you have the scale, you can actually calculate the Z. So what does this one do? So this one just gives you an example of this. If you look at this matrix, the R max is 2.12, and the R min is a negative 1.08. So that's the range of this matrix, right? And that's the matrix we want to quantize. So if you do the subtraction divided, and we want to quantize them into 2 bits. There's 2 bits. Yes. So we want to quantize them into 2 bits. And we are using the range of 0 to -2. Therefore, S equals to 1.07 because that's the this one subtract this one divided by this one subtract this one, giving S. Okay. And once you have the S, you can calculate the Z, right? So once you have because now if you look at the equation now, you have R min, Q min, S, then Z can be easily calculated. Okay, so in this particular example, Z equals to -1. Okay, so that's the way we do linear quantization. But why why do we need to want to go through all these hurdles? Like, why we are not happy with the k-mean quantization. So apparently, as I said, like for k-mean quantization, we reduce the storage, but we were not reducing the computation. So with this linear quantization, the whole purpose is that after doing this, we want to reduce both the storage and the computation. And we want to not, we don't want to use the floating point, the hardware at all. We want to replace all these floating point calculation all with integer calculation. Make sense? So let's see how to do that. Okay, there are a lot of math. So math warning. And let's see how we can, how we can replace all these floating point calculation with integer calculation, because that means that you can save significantly in terms of like both latency and energy consumption rates. So well, let's first take a look at this matrix multiplication. Okay, so let's consider this matrix multiplication weight times this x. Let's say like this is the input, this is the weight, we got the y. Okay, just let's focus on this. And when the weight essentially equals to this, when we are doing the multiplication, the weight equals to the quantized weight minus the 0 point times the scale. Right, that's the linear transformation. Times for the x, we have the same thing as sx qx minus the 0 point. Okay, and we got the result, which is sy, 2y, and zy. So quick question, is this SW and SX the same thing?
No.
Why not? So what is this SW? The scale for the weight, right? So the scale is for the weight, and this is the scale for the input x, right? So how is the scale determined? Scale equals this, right? So even we assume we are using the same number of bits to do the quantization, the range of the weight and the x, they are different. So the scale for the weight and the x should be different. Does that make sense? Yeah. So remember, this SW and S, they are two different things. So the ZW and the ZX, they are also different. Okay, so all these S, Z, they are, this X, Y, and W, they are all different. So once we have this equation, this is the matrix multiplication, and you can get, the QY, which is the quantized result, right? So this Y is quantized result equals this. Okay, so that's just simple math. If you take all this scale out, this should be SW, SX. So X should be here. Okay, X should be the subscription here. And this SY. Okay, so this QY equals this times QW minus ZW times QX minus ZX plus ZY. Okay, so that's all simple math. Yes.
So I understand how the scales are different, but you said the quantizations can also be different?
No, we can, that really depends on you, right? So we can.
Oh, okay, I thought you said that.
No, I said assume we are using the same quantization bit, the scale is going to be different.
Yeah.
Okay. For the quantization bits, you can actually choose. Later, we are going to talk about that. Okay. But no, they don't have to be the same. They don't have to be different. So once we have that, so the QY now, kind of if you expand this whole equation now, you got that. Okay, so that should be no problem at all. And then you keep doing this, and if you look at this equation, so if you look at the equation here, this QW, remember the purpose of this math here is that we want to see how we can avoid all those floating point multiplication and addition. We want to transform this math so that we can only do integer. We only need to do integer. So that remember that purpose. So if you look at the equation here, well, to get the quantized result, it equals to this. Let's forget about this for now. So you have this quantized W and quantized X. So quantized W and quantized X, both of them are integer. right? Both of them are integer, right? So this is the integer multiplication. Does that make sense? And this is ZW, remember that's a also a integer, right? The value is 0 point is also an integer. So that's also integer times a integer, okay? So ZX times QW, ZW times ZX, all of them are integer multiplication. Does that make sense? So this inside this blue box, everything is integer. It's an integer addition, integer multiplication. Okay, it's just like the multiplication are between these n bits. Okay, this quantized bits, and the addition are 32-bit. We can pre-calculate this term because the quantization, the weight, apparently we can pre-calculate. The 0 point for the z, I'm sorry, the 0 point for the x can also be pre-calculated. Okay, so only these need to be calculated on the fly when the input comes. Okay. But nonetheless, like all these here, they are integer multiplication and addition. And of course, the zy is also an integer. So everything here is integer, right? Except the yellow box. Okay. Now let's come to the yellow box. What about it? So the yellow box is the scaling factor. So SW times SX divided by SY. Okay. And remember, they're all scaling factor. Empirically, all these scales usually are in the interval of 0 to 1. Okay, that's the scale, how much we scale usually. Okay, so that's just based on empirical data. If that's the case, if all these numbers are in this range of 0 to 1, we can simply using this fixed point multiplication to do this. Because if you think about it, for a bunch of fixed point number, one thing is where the decimal point is. And calculate the decimal point, essentially, it's just a shifting operation. Does that make sense? And then like we're just remaining a bunch of integers to do the multiplication. Does that make sense? So therefore, if the range is within 0 to 1, we can convert this floating point calculation purely to fixed point calculation. And we know that for a fixed point calculation, the decimal point is essentially just shifting the bits. And the calculation essentially just fixed point multiplication, which is integer multiplication. Does that make sense? Okay, so all with me now? So therefore, now with that, the whole equation now becomes integer multiplication and addition. Well, of course, there's some subtraction as well, but all of them can be done with the integer hardware. All good? All good. So, but we are not satisfied. So, if you look at the equation, the question we're asking is that, when we are calculating the scale and the 0 point, of course, we were using that equation to try to map, right? But the question is, well, what if we just pick ZW to be 0? What's implication? Well, first, let's see what is the benefit. Okay, if we just have to, not have to, but we decide to just pick ZW, the 0 point of the W, which is the weight matrix of 0 point, right? If we just pick that 0 point to be 0, what's the benefit and what is the penalty here? Okay. If we pick 0W to be 0, ZW to be 0, you can see that, well, now this term is gone because it's 0. Okay? This term is also gone. Does that make sense? And then, like, of course, like, then we have this, and this. So, like, 5 terms now is got reduced to 2. Let me actually go do this first. Now, if we were doing that, let's assume, like, if we were doing that, now like everything got reduced from 5 terms to 3 terms. Okay, that's great. But what is the price that we are paying, right? So the price we are paying is that, well, if the 0 point were not 0, then you kind of like you have this kind of very good mapping. If you have to, set the zero the 0 point to zero, then like the scale has to be changed because otherwise it won't be like mapping, right? And if you are changing the scale, that means that the mapping may not be optimal because now you probably are wasting some of the integer bits. Because like if you change the scale, you kind of like you can map to more floating point number, but some of the bits you were never going to use them, right? So you're wasting some of them. And not just that, and also like the quantization error probably will be different compared with the optimal mapping, right? So we are sacrificing some of the quantization error, sacrificing some of the storage, but what we are gaining is the computation efficiency. Make sense? So one optimization we did is that while we think that it's worthy to pay this small price to gain the computation efficiency. Okay, you don't have to, but if you, and this kind of a heuristic optimization is very data dependent. But as long as it works for the majority of the application, people will just go with it. Make sense? So that's why we intentionally just set the ZW to zero. We no longer follow the equation. Okay, so we are paying the price of quantization error, we're paying the price of storage sacrifice, but we are gaining more computation efficiency because now we don't need to compute those two terms at all. Okay, all good. Yes.
For GX, how are we computing that? Like
So-
we can have different inputs, right? Like image one, image two, then.
Very good question. We have a dedicated part to talk about that. How do you determine the Z for different inputs? Yes, exactly. Very good. Is that the same question?
No, I was just wondering, why would we sacrifice accuracy just to save some integer multiplications? Like these are small data types anyway, so. Do you get what I'm saying? It's not a massive computational load save.
Oh,
It's some accuracy, so that's what you were saying, it depends on the data.
right. So if people find out like, we just test, well, this is one method in my head, I test that, I tried all this data out, and I think I like a very minimum accuracy drop because of the quantization error, but I gain like, let's say like 10% of the computation gain, I will do it. So it's about this trade-off. Okay, so far what we did is simply for the matrix multiplication, right? But remember, let's come back to the neural network. We also have this bias, right? So we need to plug the bias into the equation. So similarly, so we just now we add another term, this SB, which is the bias, and then also we have all these quantized, and then for the bias, we also have this scale and this 0 point, right? So that's and then we just plug this to then so remember from the very beginning the previous step we set ZW to 0, so we kind of to gain some of the computation efficiency we got, reduce the 5 terms to 3 terms. And then like come to the second line here. And then like here, if we were again, like this assumption here, if we were setting the ZB to be 0, okay, and this SB to be SW and SX, and that's even worse than this one actually, because if you think about it, for ZW, if you just set this to be 0, you can still control the scale factor to be like have a relatively good mapping. Now you intentionally not just setting the ZB to be 0, but also the SB to be SW and SX. And again, let's see what do we gain and what do we lose. Okay, what do we gain is that if SB equals to SW times SX, then we can combine these two terms together. Make sense? So now we have this one, and then we are combining this PWPX minus this plus S. Okay, and also because b equal to 0, and then, but this transformation is even worse because now, not just that you don't determine the 0, but you also not determine the scale factor, right? So the quantization mapping now totally off, and so the quantization error will be even bigger. Okay, but again, it's the trade-off. Okay, so if you do that, if we were doing this, then eventually we got this, right? Right. So therefore, for the QY, now with the bias, the QY now equals to this, and this. Again, if you look at this whole equation here, this is the fixed point multiplication we talked about. This is the integer multiplication. QB is the integer, right? Minus this, Z is the integer, Q is the integer, everything is the integer, and this is the integer. So by doing that, like everything again becomes the integer, and we only use it. We use all this integer hardware. Okay. So this one is just you could calculate it, so they are essentially the same thing. So yes, eventually that's what I said. Eventually everything now becomes integer multiplication and addition, right? So that's for matrix multiplication, usually for the fully connected layers, right? So what about the convolutional layers? Okay, so very similarly, so y equals to the convolution, wx plus bias, right? So that's the convolution layer. And if we are making the same assumptions as we made, zw equals 0, zb 0, xb equals to sw times sx, and all that, then we end up have the qy. We end up have the qy to be everything become integer operation. So this should be pretty much the same as the matrix multiplication. You can see, well, this is the fixed point operation. The convolution between a integer matrix and a integer matrix, right? And this is a integer. This is integer as well. Okay, all good. So now we show that by doing this linear transformation, by making these assumptions, now every computation now becomes integer operable. Okay, everything can be run on an integer hardware. So this one shows the decoding the decoding process. So now you can see that when you have a quantized input, which is the x, right? Yeah, this is quantized weight. All of them are integer. Okay. When you are doing the convolution, it's an integer convolution. You got an integer plus the integer quantized bias. You times the scaling factor. The scaling factor are floating points, but they can approximate by a fixed point operation, which can be carried out with the integer multiplication, then plus the 0 point, and to get a quantized output. So to get from here to here, everything is integer. Okay, so that's the hope. So now I hope I convince you, going through all these hurdles is worth the time to move from this k-mean based method to the linear quantization based method. Okay, good. So this one shows you the experiments. For ResNet 50 and the inception V3, floating point, base accuracy is this, the 8-bit integer accuracy. You can see a small drop here. But this one shows you we are paying the price of the accuracy drop. But how much, latency do we gain? Let's see. Sorry, I don't know. It's fine. So let's take a look. Let's say let's see this red dot. This red dot is a floating point network, which gives you this 60% of accuracy, but like 60 millisecond of latency. And the blue dot here kind of gave you 50 millisecond with the same accuracy. So 10 second out of 60, that's one divided by 6 is what 16% of reduction of the latency. If you can tolerate a bit of accuracy drop from the 60% to this to over here, like 58-ish, you can reduce the latency by half. Okay, so while 30 milliseconds is not half of it, it's a lot. Does that make sense? So that's why we have to desperately want to use the integer hardware instead of the floating point operations. So that's k-mean based method and the linear quantization. So sometimes we talk about different representations. We talk about k-mean based quantization and the linear quantization, linear transformation based quantization. For k-mean based, we are saving the storage but not the computation. For the linear transformation, linear quantization, we save both the storage as well as the computation. Okay, so that's the takeaway for this lecture. All right, so let's take a break. Let's take a let's say 15 minutes break. Let's come back at 7:50. Okay, 13 minutes break.